Hi, welcome back to your new lesson. This is Lakshmi Kantiwari. We are going to use a TensorFlow 2.0 with the inbuilt Keras to make a two-dimensional CNN, in which we will be using Cifar10 Dataset, and it will be a kind of image classifier. And the dataset is available at Kaggle here, and Cifar10 Object recognition in images. It has total 60,000 the training images and 10,000 for the testing, and and the size of each image is 32 cross 32 pixels, and it is RGB image, color image. That's mean the size of each image is 32 cross 32 cross 3, and the last 3 is 3 dimension is for red, blue and the green pixels to to represent its image into the color image. Perfect. So, and the another thing here new in this lesson is that instead of using Jupyter Notebook, we are gonna use here the Google Colab. Why we need to use Google Colab? Because we need to implement a deep learning algorithm. And the Google the Colab provides a free GPU and the TPU, and the size of RAM and the disk you can get from here. And it says that I think yeah, it's a 12 GB of RAM and 48 or 49. It's, you can say, around 50 GB of a hard disk. So the Google Colab provides this in a free of cost, and you can go ahead at this link colab.research.google.com. And once you open this, it will open this notebook welcome.ipnyb, the default page, and then you need to create here a new Python 3 notebook, right? So it will create a new Python 3 notebook, and although this is the online Colab, but moreover it's like the Jupyter Notebook which we have been using. And then you can change here the name of your file, and other things will be almost the same, like inserting the text, let's say. Okay, and if you want to bring this text upper, you can go ahead and move this cell upper, and then this is kind of the markup where you can give your heading. Okay, so and then here you can code. So this is how you will be working with the Google Colab notebook. Now let's go ahead and come back to the lesson. So I have already created this notebook online, so I'm going to work with this notebook, but you can work with this new notebook. Otherwise you have some other the way to to download this notebook from the GitHub repository. The link for this notebook is given into a video description, and then you can go ahead here at the file, and then you can upload a notebook. So you can upload it from your computer itself, otherwise from Google Drive or GitHub. Okay, so all these options are available. Perfect. All right, so let's come back here, and in this lesson we are gonna cover what is a CNN and the important terms of a CNN, like what is the convolutional layer, activation function, a filter or a kernel size with the number of filters, stride size, padding, max pooling, flattening and dense layer, and then finally we will start working with the download of the data and model building. So these convolutional neural network, which is in short known as CNN, is a class of deep neural networks, and most commonly it is applied into images and the visual imaginary techniques. And these CNNs are regularized version of multi-layer perceptrons, which we have seen in our previous video. And if you don't know, you can go ahead at my channel KGP Talkie. There you can see all those previous videos on a deep learning and the Pythons, and along with the classical machine learning with the feature selections. So the multi-layer perceptrons usually means a fully connected networks, that is each neuron in one layer is connected to all neurons in the next layer, right? But in the convolutional neural network, it doesn't happen like that, because in that case, like a multi-layer perceptron model or a fully connected layers, in that case the models are very prone to overfit. So that is why the CNNs are moreover the regularized version of multi-layer perceptrons, right? And these convolutional layers are inspired by biological process in that the connectivity patterns between the neurons resembles the organization of the the visual cortex. So this is how it is working, and these are, you can say, the convolutional layer, and these are the pooling layers, and then finally the convolutional neural networks have a flattening layers and fully connected layers in the last of the network. And then finally with the softmax activation function, it detects the classes. Perfect. Now let's go ahead and see what are the important terms, like what is the convolutional layer, what is the activation functions, what is the pooling layers, and what are the flattening fully connected layers. So the convolutional layers, as I said that, so this is kind of a regularized version of a multi-layer perceptron, and moreover it uses the techniques, kind of biological techniques, visual cortex technique. So there it tried to they scan an image, or the two-dimensional the data, or three-dimensional, multi-dimensional data, and nowadays the one-dimensional CNN is also coming. So it tries to they scan the data, and the size of this scanner is the filter size, and otherwise it is also known as a kernel. And then it scans, and then it tries to find out the features of these images. Okay, so then it extracts the features, and you see here these number of the layers. So these are the, you can say, the depth of the convolutional neural network. Otherwise you can say these are the total number of filters, and these things go on if you make a multi-layer the convolutional neural network. And but the data gets larger and larger as you add the number of filters more. Then what we need to do, we need to minimize the data with the minimal loss of the information. Then we come with the new term known as a max pooling. So we apply some kind of here a filter in which we see all the parameters within those filter, and then we get we extract the maximum numbers from that filters, and then finally the information get the feeded to the fully connected layers before the flattening, and then after fully connected layers, and then finally with the softmax or the sigmoid. If there is the two classes to detect, then the sigmoid can be used, but if there are multiple classes, then we need to use here a softmax or some other kind of activation function. So the question is, what is the activation function? If you remember in my previous video, I have explained what is these neurons. So this is kind of the biological in our brains. So brains are made of the billions of the billion neurons, and similarly the machine learning artificial neural network works where multiple neurons, and that's mean the multiple neurons with multiplied by the weights, the input weights, and these comes to a single points. Okay, these comes to a single points, and there with the activation functions they get multiplied, and added together. So the activation function decides where what will be the final value. Okay, so there are multiple kind of the activation functions, like here a sigmoid, which have just 0 to 1 value, the maximum, and here we have a tan h, we have ReLU, but the ReLU have a problem. If input is the less than the 0, then there is no gradient. So the another version of the ReLU comes like a leaky ReLU. So the leaky ReLU comes with some kind of the gradient if input is negative, and then we have here a max out and the ALU, these kind of activation functions. As I told you, the filter size means how many filters. See, each filters extracts different kind of the features from the image, so we need to apply there the multiple filters so that it can scan the images correctly, and it can extract the maximum amount of the information. But the number of filters should not they exceed some some particular level, otherwise your model might get overfit. Okay, and these number of filters are also known as the depth of your the convolutional neural network for that particular network. Okay, I mean the depth of the filters actually. And then here we have a stride size. Okay, let's go ahead and see what is the stride size and the padding. Let's suppose that you have these just these without the zero. So this is your two-dimensional network, and these the blue the blue rectangle, this blue square is the filter hour, and these the filter size, total number of pixels, 3 cross 3 is the filter size, and how it is moving, I mean how many pixels it is skipping, that is known as a stride size. And if you see in this, it is skipping just one one pixel. That's mean default stride size here is 1. And the padding means after this the actual data, there is 0 padded along with all those height, all those the dimensions, all these 4 dimensions. So that is known as a padding. So the padding gets added with the 0, and then these the filter goes along and it scans this 2-dimensional data, and then finally it gets multiplied by with this kernel value, and then finally it extracts these features out of these images. Okay, and these are the more relevant features. Perfect. And the max pooling is kind of it gets the maximum value. See here we have a max poolings and the average pooling. So let's say these are the square. In a square it detects the maximum number. So in this we have a maximum 20, and then with the stride size of the 2, so this move here along with this side with the 2 pixels, then it selects the maximum here is the 30, and in this square we have a maximum 112 and here 37, and similarly it is taking average of all these 4s here. Okay, now let's go ahead and see the final layer, which is flattening and the dense layer. In the CNN we definitely need a flattening and the dense layer. In between these convolutional layers and the fully connected layer, there has to be a flattening layer which transform these 2-dimensional data into a matrix, into a vector. Then finally that can be fed into a fully connected neural network classifier, and then after with the softmax or sigmoid regularizer, softmax or sigmoid activation function, then we finally can detect the final output. Perfect. So this is all about in the theory. Now let's go ahead and learn how we can download the data, and then how we can finally implement our 2-dimensional the convolutional neural network into TensorFlow 2.0. Alright, so let's start to download the data and the model building. We need to first, since we are working with the in a Colab, so every time we need to install a TensorFlow GPU, and we will be also working with the MLExtend library to plot our confusion matrix after the model training. So we need to install these 2 libraries. It's not like a typical computer where we need to just install a single time. As many number of times you reset your runtime, you need to install these libraries. But before installing these libraries, come back to the runtime. Once you come here at the runtime, then you need to change your runtime type here. Okay, so if you have a none, then you need to either select a GPU or a TPU. I have found that the TPU is a little faster than the GPU, so I'm going to select here a TPU and select a TPU and save it. So once you save it, now the backend of this Google Colab file will be using a TPU. And after that, let's go ahead and install these 2 libraries. You need to install every time. Okay, as many times you open this file, after closing this file, you need to install, otherwise it will not work. So let's go ahead and run this. It will install TensorFlow GPU 2.0 beta version. So currently we have a TensorFlow 2.0 beta version only, and it takes sometimes a little time. So let's go ahead, run this one and this cell as well. And here we have very recent version is 0.170. If you don't put this line, then it installs MLExtend 0.14 version. That is lower than 3 versions lower than the current versions, and that doesn't support the advanced techniques in MLExtend. Perfect. So let's wait for some time to install these 2 library. I think it has installed. So now let's go ahead and import TensorFlow as a TF. In meantime, we can keep writing the code while it is installing. So we are gonna here import TF sorry, we are gonna import here a TensorFlow as df, and in meantime we are gonna import a Keras from a TensorFlow. I don't think we need a Keras, so we are not gonna import Keras, but we are gonna import the sequentials model and the layers. So here we have a TensorFlow dot dot Keras, import here sequential. Okay, and after that we need to import the layers like flattening layers, dense, convolutionals, max pooling, dropouts, and wedge normalizations. I think I'll take another lessons on wedge normalization. So in this lesson we are not going to work with wedge normalization. Okay, so here we have installed our the TensorFlow GPU version of 2.0 TensorFlow, and we have installed MLXtend 0.17. We are good to go. Now we are gonna import this should be actually from instead of import. So here from the TensorFlow, so here we have a TensorFlow dot Keras dot layers, and then we need to import flatten, dense. If you are wondering how I am getting these suggestions, then I'm using kind of advanced version of Google Colab editor. You can also switch to advanced version of Google Colab editor. You need to come here. These are the new features. If it is available, then there you would get an options there. Okay, if you want to go to check a new editor, then you can just change this editor type, and I'm finding this editor is quite good, so I'm going to stay opt-in for this editor. Okay, so while on the fly it suggests you. So here we have now the dense, and then here we have the convolutional 2D, that's the conv 2D, and then we have here a max pool, the max pool 2D. So if you type here the max pool, you get so many the options like max pool 2D and the max pooling 2D. The max pool 2D and the max pooling 2D is the same thing, so you don't need to worry anything. Now let's go ahead and use the dropout as well. So these are the some layers which we will be using, like flatten, dense, conv 2D, max pool 2D, and the dropout. It says that it doesn't have sequential, so let's go ahead and see. Yeah, here it has sequential. Okay, so we have got here our layers and the Keras model. Now let's go ahead and check the version, the TensorFlow version, which we can check by tf dot and then version. So let's go ahead and run this. It should say here the 2.0 release candidate 0, which is a beta version. Now let's go ahead and import supporting libraries as well, like NumPy, Pandas, and Matplotlib. Although we don't need Pandas, but we might need NumPy, so I'm just going to import the NumPy as NP, and I'm going to import the Matplotlib dot pyplot as PLT, and I'm going to also import Matplotlib. We will be needing this Matplotlib during the plot of our the confusion matrix. Perfect. Now let's go ahead. So we have imported the necessary packages. Now we need to download the data. So we are going to work with the Cifar dataset, which we have here at the Keras, but we are not going to download from the Keras. The TensorFlow 2.0 automatically have it, the Cifar10 dataset. So we are going to download that from Keras datasets itself. So that we can download from Keras, from TensorFlow dot Keras, and then dot datasets, and then here we have import, and then finally here we have Cifar10. Perfect. So we have imported Cifar10 reference. So let's go ahead and download this dataset, which we can download this dataset by calling the Cifar10 then dot load data. So it will return a tuple for training and the testing. So we will get two tuple here. So the first tuple is for training, another tuple is for testing. So let's go ahead and read this data into x underscore train and y underscore train, and then finally x underscore test and then y underscore test. Right. So let's go ahead and load this data. So it takes a little time to download a complete data. In meantime, you see here this data set have a 10 classes, and Cifar10, these last 10 represents that it has a 10 classes. If you come here at the data, it might show you. Otherwise, yeah, I think it has here. So these are the 10 classes, which are the airplane, automobiles, bird, cat, etc. So we are going to create here a list of the classes. So there the classes name, and we are gonna create these list like we have here airplane, images of airplane, and then here we have images of the automobile, and then we have images of bird, as well as we have images of cat, and then we have images of deer as well, and the images of dog, and then finally we have images of frog, then finally we have horse, and sheep and the truck. So here we have sheep, and then finally we have a truck. Perfect. So these are the classes which we have in our Cifar10 dataset. We have already got the training and the testing dataset. Since these images which we are gonna use have the maximum value which is the 255, and how you can get that, you can write here x underscore train and then dot max. It will return you the maximum value present in this training dataset, which is 255. But the artificial neural networks in general, the preferred value is closer to 1, since we have seen into our the activation function. So mostly the value we get the maximum gradients when values are somewhere nearby 0, okay, or 1. So that's why we prefer mostly if values are almost nearby a 0. So moreover, we would prefer if it is in between somewhere 0 to 1. So what we are going to do here, we are going to divide our X train data set with the 255 so that the maximum value should be 1, and similarly we are gonna divide our X test data set with 255 as well. So now maximum value has come under 1. Now let's go ahead and check the shape of these data sets. So here we have a shape which should be 32 by 32 and then 3. So this is the shape of each images, and this says that we have total 50,000 images. Actually, I'm sorry, initially I told you that we have 60,000 images, but we have actually the 50,000 images and 10,000 images for training purposes. Right, so which we can check here with xtest.shape, and there it says that we have 10,000 images, and each images have 32 cross 32 width pixels, and each pixels have 3 depth, which is RGB. That's mean each pixels are color pixels. Now let's go ahead and see some images, how we can see those images with the plt dot imso. So with these imso, which is image so, with this we can pass here the first value of x test or x train whatever with the 0. That's mean it will show a first image. So here you get this is a bird. Actually, how would you make sure that this is a bird? You can print here y test, and if you print y test, you see a first level is 3, and the 3 is, which one is 3? It is actually the cat. Okay, so this is the 3. Since it starts from the 0, that's why this is actually a cat. Okay, so this array starts from 0 to 9 maximum. Okay, so it says that it has a 3 there. Perfect. So now let's go ahead and build our CNN model. And before building CNN model, let's go ahead and insert few cells for coding. so that we can get enough space to code. And before that, I'm gonna insert a text here where I'm gonna write build CNN model. Alright, so here I'm gonna build a CNN model. So building a CNN model is fairly simple. We need to first get a sequential object here. So once we get the sequential model, and then we are going to add here the convolutional layers, flattened layers, and the dense layers. So the model dot add, and then here we have conv2D. Okay, so here we have a convolutional 2D. Inside the convolutional 2D, now you see it asks about how many filters do you want, what should be kernel size, what is a stride size, what would be the padding, and what will be the data formats, etc., and the activations as well. So these things we can pass here. So let's go ahead and pass these information. So the first we are gonna pass here filters. How many filters we are gonna use? We are gonna use initially 32 filters. So it is up to you how many filters you want to use. Moreover, it depends on testing and the trial error. So you need to apply a multiple type of the filters with the multiple size. Then you can select which one is giving maximum results for your task. So let's go ahead and fit a kernel size which is 3. Here if you give just a single name 3, then it will make a 3 by 3. Otherwise you can give here a tuple like a 3 by 2, okay, as well. So let's go ahead and make it a simple here. So we have here a 3 cross 3 kernel size, and now here the padding which we are gonna use, instead of valid we are gonna use the same padding here. And then the activation function, we are gonna here use a ReLU activation, and the input shape. Okay, so input shape, we have initially how many input, what is the shape of our input? That is a 32 cross 32 cross 3. So we have 32 cross 32 cross 3. Right, so these are our input shapes. So we have built the first model. Now let's go ahead and run this and see okay, what happens. It says that there is error, perhaps. I think yes, we need to close this one as well. So now you see we have here added the new convolutional layer. Perfect. So now let's go ahead and actually the best practice to keep all those the model building at the same in the same cell. Otherwise sometimes what happens, if you run a cell multiple times, so it get disturbs. And now we have added the first convolutional layer. So let's go ahead and copy this and paste it here. And since we are going to add the another convolutional layer, that will be the inside. So in that case we don't need actually the input shape. Okay, so in that case we can delete this input shape. So let's go ahead and delete. Why? If you see these convolutional layers, so these are the first convolutional layer where we need to define what is the input size, but after that we don't need to define the input size. All right, and now we are going to apply here a max pooling. Okay, so have we imported the max pool? Yes, so we have a max pool and the dropout. Okay, so let's go ahead and add a max pooling as well, so that we can reduce the overhead. So here we have a max pool 2D, and the max pool 2D, it asks about what will be the pool size. Okay, that's mean what will be the size on which we are going to look for the maximum value. So the pool size we are gonna use here a 2 cross 2, right? And then what will be the stride which we are going to use? So the stride size I'm gonna use here 2, and then it asks about what will be the padding. Okay, so I'm gonna use padding is the valid padding, right? So in case of the valid padding, it tried to reduce the dimensions, but with the same padding it tried to keep the same dimensions on which we are applying the filter. So we have max pooled the data. Now let's go ahead and apply a dropout. So after a max pooling, I'm also going to apply a dropout. So the dropout, what it will do, it will try to, it will try to make sure that the sum cell in a convolutional layer gets die out. Okay, so that it should not overfit actually. So the dropout actually prevent overfitting. Right, so we have here a dropout in which I'm going to drop 50% of input, so that is 0.5. So the 50% input will not be considered while calculating the next stage. Now let's go ahead. So here we are going to just use the 2 layer of the convolutional layer, and I'm now going to add a flattening layer. So here we have a model dot add, and then here we have here a flattening layer with a flatten. And after this, I'm going to add finally a dense layer. Okay. So we have a model dot add. We have got our flattening layer. Now I'm going to add here a dense layer. So the dense layer asks about multiple input parameters, like how many units. That's mean how many neurons we want. We want, let's say, the 128 neurons, and then it says that which activation function we want to apply on these fully connected networks, which is also known as dense network. I'm going to say that we want here a ReLU. So on this activation, on this the fully connected layer, I have applied here ReLU activation function. Now let's go ahead and add a final output layer. So in output layer, we need to keep the units which will be equal to number of outputs. So here we should have units is equal to 10, since we have 10 classes to predict, and then the activation function we should keep here softmax. We cannot use ReLU, we cannot use sigmoid, and we should use here softmax. Why we cannot use a sigmoid? Because sigmoid can predict only the binary prediction 0 or 1. So here we have a softmax. Finally, we are done with building our model. So the model has been built. Let's go ahead and print the summary of this model, which we can print with model.summary. And in this, you see, this is the summary of our model. So we have here 2 convolutional layer, and then finally we have a max pooling after second convolutional layer. Then we have a dropout. After that, I have added a flattening layer, then dense layer, and then finally output layer, which is also a dense layer, kind of. Okay. So this is one of the very simplest convolutional neural network. If you want to add more, then what you can do, you can just copy these 3 lines and you can paste it here, and you can keep pasting. You can increase the size of your model. Okay. Right, so although but as of now we are going to just go ahead with this simple model, so that it should not take much, the training time. Otherwise we need to wait for much larger time to complete the training if we make a complex network. Now let's go ahead, compile our model. So we can compile our model by calling model.compile, and there we need to pass what is the loss, what should be the optimizers, and what should be the metrics on which your model should be optimized. So I'm going to first pass here the optimizer, and I'm going to use here ADAM optimizer, and then it is asking about what should be the loss. Okay, so I'm going to use loss which will be a sparse categorical cross entropy. So here we have sparse categorical cross entropy. Then finally it asks about what should be the metrics on which we are going to calculate the output of we are going to optimize our model. So the metrics on which we are going to optimize our model is sparse categorical accuracy, which we can get by here sparse categorical accuracy. Perfect. So let's go ahead and compile this model, and after this, now the most exciting part of this convolutional neural network is model fitting. So once we type here model.fit, there you see it asks about multiple parameter like x train and y train, the batch size and the epochs and the verbose. So what we are going to do here, we are going to the pass here the first x train dataset on which the training will be done, and then y train by which it will be compared, and then I'm going to pass here the batch size. I'm going to pass here a 10 batch size, and then it asks about how many epochs we want. So here I'm going to pass a total 10 epochs, and then it finally asks about the verbose. Okay, so here I'm going to pass a verbose is equal to 1. That's mean it will keep printing the progress of our training model, and then I'm going to pass the validation data as well. So what should be a validation data? That's when during the training it will also keep validating our model. Okay, so for a validation data, what I'm going to pass here, I'm going to pass here a tuple. That's mean the x test and the y test will be used for a validation. Okay, so this is the all information, and other informations we can neglect, right? So one more thing, if you see here, our model.fit returns a history of our trained model. Okay, so to record that history, what we can do, we can just record that history if we take that parameter in history. So after the training this model, then we will be getting all the history for each epoch, its training accuracies and the loss for validation and the training set. Then finally we can plot the learning curve of this model as well. So let's go ahead and hit the enter. It will take some time to complete the training of this model, so we need to wait to get it done. So it might take about an hour to complete this training, although we are using a GPU. So this was the difficult to train on your computer. So if you are using a computer, please don't run it in your computer if it doesn't have a GPU. If you are working in the CPU, then it can't do. You need to come back here at the Google Colab where you can apply the GPU on this training of CNN model. So let's go ahead and wait for some time to get it complete. Alright, so our model has been trained here. So we had selected a batch size 10, epochs 10 and verbose 1, and this is a complete verbose to our model, and it says that here the maximum training accuracy it has achieved 80.65, but if you see here a validation accuracy is just 70.28. This is the difference, okay, in between accuracy, the training and validation accuracy says that our model is overfitting. If validation accuracy is less than training accuracy, then the model overfit, and if validation accuracy is the more than the training accuracy, that's when our model is underfitting. So in this case our model is overfitting. So let's plot our this learning curve against the loss and accuracy of a training and validation set. Then let's understand with this loss how these models are overfitting and at which training epoch model started overfitting. Perhaps after fourth epoch, here you see the fourth epoch which we have, the training accuracy is around 70% and here it's around the 68%. And perhaps after this, after the third epoch and between the fourth epoch, the model started overfitting. So let's go ahead and plot this and see how it is overfitting. So we need to plot it in the matplotlib. To do that, what we need to do here, we need to the call matplotlib.plt function. So I have already written the code, since this is a very traditional code. And if you don't know how to plot plotting in the matplotlib, then what you can do, you can to go ahead my matplotlib tutorial here, and I have shown there a detailed the matplotlib tutorial, and you can learn more about the matplotlib. So let's come back to this cell here. let me explain you the epoch range which we are taking here. Since this is a 10 epoch, so we should take here 11. The range will be 1 to 10. And here we are plotting epoch range against the 1 to 10. That's mean here the epoch which we had selected for those number of epochs for which we had trained our model. And here you see the history. So the history returns it's kind of the callback which records all these information. That's mean the losses and accuracies of the training set as well as for validation set. And then the history. So this is kind of the dictionary, the sparse categorical accuracy. So I mean these values is there, and validation sparse category accuracy. These values will be, you know, the recorded actually in these variables. And then these are just the title and the Y and the X level along with the legends. And then here the same we are doing for a loss as well. History with in logs in the dictionary, and the loss keys and the validation loss key is representing the loss of the training and the validation set respectively. So let's go ahead and run this cell and see a plot of learning curve. So here we have a plot of the learning curve, and in this you see the accuracy of a training set is kept increasing, okay, for each of these epochs, but the accuracy for a validation set, it has came to you know, the below than the training set after the third epoch. That's mean it is saying that the accuracy validation accuracy is less than the training set. That's mean the model is overfitting. And here with the loss you can also verify that a validation loss has you know, saturated after the 3 epoch. That's mean the model is not learning, but we had you know, we kept running our model, and I mean we kept training our model, and the training error has you know, the training loss kept decreasing, but the validation loss was not decreasing. This says that our model is overfitting. That's mean we had increased the complexity of our model, but it doesn't learn actually, you know, generalized. It could not generalize actually. And one more thing, you can make the changes here in the model. You can copy and paste it, and you can similarly change the dropout layers and the filter size, stride size, the kernel size, or the filter size, and then finally you can retrain this model. I had taken this simple CNN model because it takes a lot of the time. It has taken almost 1 hour in my, you know, this Colab. The notebook, it will I think will take almost the same time in your Colab as well. So that's why I had taken just a small and simple CNN model for this. So let's go ahead and plot a confusion matrix for this. To plot a confusion matrix, as I have already told initially in this video, that we need to install MLExtend library. So let's go ahead and import plot confusion matrix from MLExtend library. So from that we need to write here MLExtend dot the plotting, and then we need to write here import and then plot confusion matrix, and then here from sklearn. So here from sklearn.matrix import the confusion matrix. So here we have a confusion matrix. Now we are going to import the matplot. I think I have already imported the matplotlib, so I don't need to import that one. Now let's go ahead and import now let's go ahead and do the class predict. So what we can do here, we can call here ypred is equal to the model and then dot the predict classes, and for predict classes we need to pass here x underscore test. So in now ypred it will predict the classes, and then in y test, the y underscore test is the original class predict original the result you see here. And let's go ahead and the print ypred here, and if you see the vibrate there and here the original class, so it says that the 3.8 the correctly predicted, but the 0 here the prediction is wrong for this one. So this is how we can see the y test and the vibrate. Now let's go ahead and plot a confusion matrix in just a 3 line of code. We can do it very easily. The mat is equal to the confusion matrix here, which we had imported from ML extend library. It takes the y true, which is y test, and then it takes y pred, and then finally it takes yeah, so this is all it takes. Now let's go ahead and get the confusion matrix. So with this we have got the confusion matrix which is into the mat. Now you can see this is a confusion matrix, and with this here you see the label as well. There we can also pass here a label which is actually the classes names. With this label I think the label is not true here, so let's just delete it. We will pass this label while plotting the curve, while plotting this the confusion matrix. So we have here the matrix. Let's go ahead and plot it. This is really very simple. In one line of the code we can plot this. So here we have a plot, and then underscore confusion matrix, and there you see a input. It takes a input confusion matrix. In that confusion matrix we need to first match, and then hide spine. We don't need to give any parameters there. Let's go ahead and set a figure size, and I'm going to set a figure size 12 by 12, and then after this it takes the input like the classes, and here we take classes names is equal to the classes names, and after that it also takes few other inputs, but we are not going to pass that. Let's go ahead and see the confusion matrix. All right, so here you see the confusion matrix. I think the plot I have plotted it the quite large plot. Let's go ahead and see it into the 6 by 6 plot. So with this confusion matrix we can also see the classes here, and this is a predicted class and this is a true label, and we can also get here the probability, I mean the accuracy for each classes, that we can get with the so normed is equal to the true. So if I write here so normed is equal to true, then we will also get the probability for each classes. So we can also increase this by 9 by 9. Let's see 9 by 9. Then there would be a larger figure there, and now we can see the accuracy for each classes. So with this you can see the maximum accuracy which we are getting in these SIP classes, the truck and frog, etc. But the lower accuracy has been reported for the cat, and for a dog, and for a bird. So these are the lower accuracy, but for others the accuracy is quite good. Okay, and now you see here the cat, this is the predicted and this is the true label. So let's say if the true label this is the predicted one and this is the true label. So with this it says that here the true label for the airplane, okay, and the predicted label is for airplane is you know, it's around the 687, that is the truly predicted. But for the airplane, the 23 airplane has been predicted as the automobiles, and the 59 has been predicted as a bird, and the 21 airplane has been predicted as a cat. So these are the error actually for the airplane. But if you see here the automobiles, okay, so these are the automobiles. Here it has been, you know, the predicted the wrongly, you know, 136 automobiles. This is the true label. So 136 automobiles has been predicted as a truck, and you see here the 199 cat has been predicted as a dog, and now you see here 182, that is 18% dogs has been predicted as a cat. So this can be, you know, the intuitive, as a dog can be predicted in the cat, and the cat has been predicted into the dog. Right, so but you see here the accuracy, you know, the misclassification in the dog and the automobiles is really very low, right? So with this you can understand the meaning of the confusion matrix. So this is all about in this lesson. So in this lesson you have learned so many things. The first, you have learned what is the CNN and how it works, And then you have learned how you can install the TensorFlow GPU and ML Extend library, and then you have learned how you can build your CNN model, and then finally how you can train it, and then finally how you can draw the learning curve and the confusion matrix in this lesson. So thank you so much for watching this video. Please do not forget to like and subscribe this channel. Bye bye. Have a nice day.